Hi there guys, well welcome back. This is 5I. This is the last section of your statistics here in chapter 5 or unit 5. This is about correlation, causation and linear regression. Okay, there's quite a lot to discuss here, but in fact a lot of this is using massive formulas which are actually in your calculator. So most of this is going to be a kind of a light touch on this, just because you should be aware of these things, and actually these things can be quite useful when it comes to doing coursework as well. So it's kind of useful, but we're not going to do it into too much depth at all. So let's just discuss a little bits and pieces here. So it says correlation to start off with. So this is the first thing. This is the first thing we're going to deal with. Then linear regression second, and then causation is kind of just sort of discussed at the end. There's like several points which you just need to discuss through. Does one thing cause another thing? Well, first of all, what are we talking about? We're talking about scatter graphs. So we're not talking about functions here. We're talking about getting a whole lot of bivariate data. Bivariate means there's two variables. So there's an x and a y, and somehow, hopefully, they're related. Now, if I put some more in here, starting to look like there's a bit of linear correlation here. So linear correlation is talking about straight line correlation. Now, most of you will have done a line of best fit before and said, well, doesn't look like good correlation here, but it seems to be kind of going in this direction, kind of like this. And so a bit like, I kind of think of it like a whole load of tins stacked up in a supermarket. And, you're driving your trolley at these things here, and you drive right for the center. And, and when you drive right through the center, you're going to get things scattered on either side, equal amounts scattered roughly on either side, okay? Right, so what we want in this case is roughly half the points to be on one side, roughly half the points to be on the other side, and roughly to make a line of best fit, to make that line of best fit roughly in the center in the right direction. Okay, now actually I'm now talking about linear regression. So in making the line, that's linear regression. Now there's some mathematics in order to make one, rather than by best fit kind of trial and error, if you like. There is some mathematical formulas which will allow you to make that line. Okay, and they're in the calculator. Now, in terms of correlation, we need to know about another formula, which is the Pmcc, which I discussed right back at the start of this unit. And I said, well, sometimes it's called Pearson's product moment correlation coefficient. But often now they drop P because Pearson's a bit of a controversial character. So we're talking about the product moment correlation coefficient. Now, this gives you a value which we call, in this case, we call R. Okay, now you'll see on your calculator that you also get R squared. Now, I'm not going to go into too much detail there, but R squared is often used for nonlinear relationships, and if we're talking about linear relationships, we'll be talking about the Pmcc being equal to R, right? So this is our correlation coefficient. Now you can see that you have some sort of positive correlation here, but it's not that strong. Strong correlation would be all of the points really, really close to your line. Now, in fact, if they're all on your line, that would be 100% correlation. Well, what value should we use for that? Well, we can say R is equal to 1 if all of the points are on the line, and it goes in a positive direction. Even if it's just a little bit positive in direction, it would still be +1. Okay, now if we go, let's do steep, negative, and it goes through all the points. What would you be expecting there? Well, R in this case gives you -1. Doesn't matter if it's like this as well, and they're all along the point, all points are all along the line or not. Okay, it just matters if it's going downwards, and if all the points are in the same direction, then you'll get R is equal to -1 for the Pmcc. Okay, right, now values in between will show you moderate correlation. So for example, if you get 0.5, this might be an example of getting R as 0.5. We're saying, well, it's kind of moderate positive correlation. It does seem to be positive, and it's moderate. Okay, but we don't just guess these things. There's actually a calculation for these things as well. So there's a formula behind this too. And we're going to have a look at that through this exercise. Okay, now it's important to note as well, so we're still on the topic of correlation here. It's important to note as well that you can have correlation which is not necessarily linear. You might have all your points making some kind of quadratic shape. Now, in this case, if we apply our formula for this Pmcc, the product moment correlation coefficient, or simply our correlation coefficient, or simply we try and work out what R is, it won't be able to say that there's an R of 1 here, even though we can see that there is a clear correlation. It's a quadratic correlation. It won't be able to give this because the formula depends on there being linear correlation. So in this case, it will probably say, there's zero correlation. It will say R is equal to 0. We can't see any linear relationship. So, or something near to 0, you know? So, you know, for this, there's another technique. If you want to go beyond linear, your calculator can do this. You just need to say the relationship which I'm defining is quadratic. How close are we to this? And it will give you an R squared rather than an R value. And that's great. And that could be useful for coursework, but that's not what we're doing now. We're only looking at linear correlations. But it's important to note that there could be other relationships where there is correlation. It's just that the statistic which we're going to use won't necessarily find that. Okay, well, let's look at the book then. So it's talking about scatter diagrams, that's what we're mentioning. 2 quantitative variables from an individual set of data being plotted. You know, we could be plotting an individual's height and weight, for example. So any object, if you like, which has 2 associated data points with it. You know, you could, for example, be talking about a particular day in August, and you could be taking the hours of sunlight and the temperature. You know, so you just any particular thing which has got a 2 data points attached to it. Okay, so they're saying here, when you describe a scatter graph, you should be looking for patterns, as it's important to classify your observation as association. Is the pattern positive? In other words, does it move upwards from left to right, or is it a negative association? What about the form? Is it a linear pattern? That's what we were talking about. Or is it a quadratic pattern? And what about the strength? Is it strong? Is it weak? Is it moderate? Okay, so, you know, there are options there before we do any calculations for this correlation coefficient. Okay, so here we go. Here's correlation can be positive in the graph there, which we're looking at in the left, top left. Negative, and you'd say that both of those would be strong positive and strong negative. And it looks like no correlation on the top right. Maybe there's some negative correlation there. Maybe extremely weak negative correlation. I'm not sure, but it says no correlation. It says correlation can also be described as strong, moderate, or weak. So there we go, strong, moderate, and weak. And here we go. The correlation R measures the direction of the association and the strength. It can be given as a verbal explanation or a numerical quantity. So let's have a look at this one. Now, they're talking about this now, building up a mathematical formula for the correlation. And a bit of international mindedness there about Oliver Lancaster, Australian statistician, made the first convincing case for a link between exposure to sunlight and skin cancer. Okay, well, there's an investigation there which you can have a look at. I'm not going to do that now. And we've got here we go. Regression requires an explanation variable and a response variable. Now it's talking about linear regression. Now, so they're skipping a little bit here, right? It's kind of annoying. So now they're skipping into something else. What we really want to deal with is this Pmcc, right? That's what's really important here. And we want to know, here we go, we want this. We want to know for this correlation coefficient, the Pmcc, it ranges from -1 to 1. -1 is strong negative, 1 is strong positive, and you can see things in the center there. You're going to need to use that language. Very weak, 0.25. Weak positive, 0.5. Okay, now some questions will say express the correlation in words, and some won't. Now, what I'm going to just show you here is kind of the long way around in terms of these questions. So actually, let's look at example 12. And example 12 gets you to find R through some tables, and it never gives you the formula, which is really frustrating. But the formula, or at least not until you get to the question. So the formula is this thing here. Let's zoom on in. Okay, finally got there. The formula is this. So this is what we're going to need to do. Okay, we're going to need to do SxY divided by Sx and Sy. Well, what are these things? You know, what are these things that we've got here? Well, Sy comes from sigma sigma y. Okay, now let's just have a little look at what they're calling. Yeah, so that, yeah. Okay, so they're allowing the n in there. Yeah, okay, so just checking. So Sy is it's saying this is our standard deviation in terms of y. This is standard deviation of y values. And of course, Sx is similar. Then what's this question? The question is, what's this thing here? Well, this thing is our covariance. Okay, it's, you know, this is looking at, we need to look at the formula for this, okay? And I'm maybe not going to be able to give full explanations for this, but it's saying we're going to do the sum of your xi minus x bar, and then times that by, now instead of squaring it, we're going to times that by yi minus y bar. And then you're going to divide by n. So that's your covariance here. Okay, so this is going to be your SxY. Now, in order to get a sense of what that's kind of creating, you really need to take some coordinate points. And you can say, well, look, you know, here's our coordinate point on the graph, x bar, y bar. And we know that that's going to be a middle point, which we can put on our line of best fit. And then in order to think about what this is giving, let's just take any point. Let's take a point. Let's take a point over here, which is just keep everything positive. Let's take this point x1, y1. Then what this is giving is a kind of rectangle. It's saying, well, what's the difference between x1 and x bar? Well, it's this difference here. And what's the difference between y1 and y bar? Well, it's this difference in height. When you times them together, you're kind of getting this. So you're not squaring your differences, you're squaring, you're finding this rectangle, if you like. Now, it's just a definition, and, you know, there's perhaps other ways of doing these things, but this is a really neat way of finding a value for R. Now, I don't have the answers as to why this exists, really. Okay, I'm sorry for that, but the book really isn't explaining this in great depth either. But just a physical explanation or a geometric explanation of what the covariance is it's basically adding together all of your rectangles. Okay, so, you know, obviously if the points are further away from this thing here, your x bar, y bar, then these rectangles are going to be much bigger and your covariance is going to be much bigger as well. But it's basically like a variance in 2 dimensions. Okay, so let's look at this thing again. So that's going to give you R, and luckily R then comes out, or actually by design, in fact, R comes out giving you values between -1 and 1. Okay, so now you basically can just do all of that information from, you can calculate R from this table here. Now, of course, your calculator calculates this for you, and on your calculator, you only need to put in these two categories here. But remembering that if we want Sx, for example, we need to do the sum of our x squares divided by n minus x bar squared. That's the variance. And we can square root it to get the standard deviation of x. Now remember that that's the other alternative formula than the formula which is x minus x bar for each of your points. That's your other formula. But in this example here, they're using this version of the formula for the variance. Okay, so sum of all of the x's there, sum of all of the x squareds there, sum of all of the y squareds, sum of all of the y's, and then the SxY formula. Now I wrote it down as x minus x bar, y minus y bar, all over n. Now we don't need a squared on there, in fact, because yeah, we don't need to actually square root this. This SxY is just this. Okay, don't know if I'm being convincing there. Let's look at this formula here. There's the covariance formula. And let's look at what they're doing in the book for that one as well. SxY, yeah, they've got SxY is kind of like saying, well, look, we've already done the x times the y. So this is just SxY with the two variables next to each other. I mean, it is still this covariance, but we don't need the squared on. The squared is really saying, look, we're doing x against x here. Whereas if we're doing SxY, it says we're doing x against y. We don't need the squared there. Okay, so SxY is this thing here, but there's another format for this, and that's to say, look, you can do your sum of your x, y's all over n, okay, and then minus your x bar, made a mistake on that formula, didn't I? Y bar. We subtract that off the end. Now, again, I'm not proving that, but that could be proved in a similar way to how we did the previous proof to get to this one here as well. So we've got this format here. So now all we need is this column, our x, y's times them together, and the sum of those. So there we go, we've got the sum of the x, y's divided by n. And we also need our x bar and y bar, but obviously we need those for the other situations too. Now, once we've got that, we can actually work out what SxY divided by SxSy is. That gives you your R, and you are done. Now, that's how you do it in a longhand method. But from my point of view, I think you should be aware of these formulas. It's not difficult to remember this thing here. And although that's not given in the formula book, it is mentioned here. It's not difficult to do, and it's kind of good to have a go at least at one of these questions, or potentially an exam question will give you this. It will say, look, we'll give you all this information. We'll tell you that there's n terms. Now go and work out what R is. Now you then can't put your data into the table, but you can use these formulas here in order to work out what R is. So that's why it's a good idea to know what the covariance is, and it's good to know what the R is as well. And it's a really simple formula. It's the covariance of xy divided by your standard deviation of x and your standard deviation of y. Let's have a little look at how the book does it again. So we've got s squared of x there, sx squared there, so that's your variance. And obviously they're going to square root that in the R version there too. Okay, well, I think I've said enough on that. It's maybe worth working through that kind of carefully to see what's happened. But obviously you can get this from your GDC by coming up with your table of x, y, and then you go to your stat calculations, and this is just given in your one variable statistics calculations. No, it's not. I'm wrong there. This is given in your two variable statistics calculations. Okay. Yeah, because obviously we've got two variables. Right. So example 13. So things seem to be the wrong way around a little bit here, because they've also talked about least squares regression. So they are ditching a huge amount of mathematics here on you in one exercise. And normally this would be split up into at least two exercises. Now, least squares regression. How does this work? So when we get, let's do it through this diagram, because this diagram is pretty nice. Okay, so least squares regression analysis is basically saying, let's make from each of our points a square by taking that point to the line and then squaring it. So basically we're squaring our residuals there. Okay, and then let's try and minimize the sum of the areas of these squares. And we're going to minimize the sum of the squares of these squares by putting the line in the right place. Now, again, I'm not going to be able to explain that one fully, but that's kind of the concept. And so if you put the line somewhere else, you'll see that you'll get much bigger squares. And there is an optimal place to put this line, which reduces our number of squares. Now, that's actually going to use, let's look at the formula for this. That is going to use similar things to what we were dealing with before. So if you look here, they're talking about your M. So this one here is quite good. So let's look at this. So let's open the image in a tab here. Let's just zoom in on this one here, okay? So let's check this thing out here. Actually, let's actually copy this thing. No, I've already copied that. Let's just talk about it, okay? So here are the formulas which you need to use for least squares regression. Now, M here is considered to be like your covariance of xy divided by your variance of x, but your n's have cancelled. Okay, so this really is your covariance of xy divided by your variance of x, but because they both have divide by n, the n's are going to cancel there. So that's still the same thing in this formula, really. This is SxY divided by Sx squared, a variance of x. Now that's different to R, and we're only doing this in terms of x here, whereas sometimes we do it in terms of y, and we need to discuss that as well. Now they're saying, well, we can set up the equation here. We can find c, so we need a y equals mx plus c, but we can set up the c by putting in x bar and y bar into our y equals mx plus c. So once we've found m, we can work out c by doing y bar minus mx bar, because we know that x bar and y bar should really fit in the middle of our data, so it should be on our line. Okay, so there's a bit of the theory behind it. Now, there's a bit more to this as well, because there's actually two formulas, and one works when we're making predictions for y, and one works when we're making predictions for x. Now, again, you don't need to go into too much detail there, to be honest, because the book only does it one way, and we'll have a look at that next. But in terms of the theory, which is what we're talking about here just for the moment, we're trying to reduce the size of these squares, and we do it through those formulas. Now, these squares here are actually, so we're not reducing the size of the rectangles, which would be kind of nice, right? But these squares are saying, well, look, if you put in your x value here, then what is the difference of the y height? So it's the y residual here. So it's y from the line, take away your, and let's call this x1, and let's call this point x1, y1. So it's saying, well, what's the y from the line? And let's take away y1, so let's take away that height, and let's square that. So this version is talking about minimizing the squares from the point of view of y. So it's minimizing the y errors. Again, that's kind of a little bit of the theory, although again, that's not a proper mathematical explanation. But this is minimizing the y errors. So when we're putting in x, we want to minimize our y errors. Now, an alternative way of doing this thing here would be to minimize the x errors. So if we take, for example, this is our y1 point, and we put that in here, and let's just take another point here, right? Let's say that this is a coordinate point, and this is x1, y1. And then to get to the line, in the y direction, we'd be actually going all the way over here, and, you know, we'd be getting a massive difference from that line. In fact, we'll be getting, that's going to be our x residual there. That's the x value from the line, take away the x1. So this is the x residual. You can see that's going to be huge. So there's a different way of doing this the other way round. But in fact, they both give you very similar lines. Just the gradient might be slightly different, but they're both going to go through some middle point, which is x bar, y bar. Okay, so it depends on what the independent variable is. And maybe we don't even have that. But if we're trying to show that one thing, or if we believe that one thing causes another thing, then the thing which we believe causes the other thing, so our dependent variable, we'll have to use this formula one way round in order to minimize the y errors, if you like. Okay, right, let's just have a look at some questions. So they're saying this in here in the book as well. So they're saying the vertical deviations, this is the last paragraph here. This is called least squares regression. And they're saying the vertical deviations are considered, then the line becomes, if the vertical deviations are considered, then the line becomes the regression line, line y on x. So x being independent, where x is the explanatory variable or independent, and y is the response variable. It's what comes from the thing which explains y. Okay, and that's the most frequent form of regression line, and that's the one which we're using. Okay, in the horizontal deviations minimized by the line become x on y. So that's what I was talking about. Okay, there's a graphical illustration here, and a calculator can identify each case of the data points. It calculates x, y, and places the line through this point. Calculates x bar and y bar, I believe, and then measures the vertical distance. Yeah, okay, basically what we were talking about. There's nothing too much more there. The line is pivoted. The line is then pivoted until the sum of the areas of the squares is at the least possible value. Okay, now once the line has been generated, the equation of the line can be calculated, right? So look, they're not giving you here any formula for this. So you don't need to worry about this formula. It's not turning up in the book. And in fact, when it comes to just using your GDC will do it one way around, and it will do it the way we want it. So we're going to put in our explanatory variable or our independent variable first. So all that discussion about x on y, y on x is just theory, and it's not really what you need to know here. What you need to know is how to put numbers into a table. Okay, so put in your English, for example, put in your humanities scores as your y, your second line in your table, and then you're going to do a linear regression. And in fact, let me just do it here. I've got my calculator with me. And if we were going to do that, we go to statistics, we go to statistics calculations, and then we go to linear regression. And you'll notice that there's two versions on the TI Inspire. Maybe there is on your calculator as well. And that's mx plus b and a plus bx. And in all of the linear cases I've tried, it gives exactly the same thing. So just use either or, it doesn't matter. Okay, so I would suggest that you now spend a little bit of time putting in your values, your English values in your first column in your calculator. Put in the humanities into the second column. use your GDC to then say, let's do some stats calculations. Let's look at linear regression, and it will give you an mx plus b or an ax plus C. I can't remember which way around it was, but it's really obvious, okay? And it will tell you what your values are, basically. It will tell you what your coefficients are, depending on the model that you've got. Now, that's done. Okay, so we're doing this via the GDC. Now, a little bit of a hint, there we go again, which we looked at before. That was the R. That's done. And there's another example here. Okay, and this exercise goes on, right? There's more discussion towards the end as well. So let's look at example 13. If you want to take a quick break, get a cup of tea, then go ahead. Let's look at the example 13. And this one says, a student obtained a mark of 75 on an English paper, but was absent for the humanities exam. Justify using the data and regression line from the previous example. Justify using this to predict the grade he would obtain on the humanities exam and find his exam grade. Okay, predictions of exam grades. When is that ever going to happen, hey? Right, so how do we do this? Well, we've got an equation now. We've got this y equals mx plus c from the previous part. So we just substitute in 75 into this and we'll get an answer out for our y. That says if another student was absent for the English exam and his grade on his English exam was 20, state with a reason if it's justifiable to predict his English grade using the regression equation. Well, two things. This regression equation has used English as the explanatory variable. So English is our independent variable here. And the formula uses x as our independent variable. So first of all, there's an issue of the fact that we've minimized our y residuals from this within this formula. So in going backwards, we really need to be reducing our x residuals essentially. So there's a problem in terms of the formula because the formula assumes that English is the independent variable. And so, going backwards is we really should use the value. We really should set up another version of this on our calculator with humanities first. And also we need to talk about the correlation coefficient here. Is it justifiable? Well, it depends on how close correlation is. If the correlation is really close, then if it's nearly 1, then yeah, sure, this would be a really good idea. Whereas if in fact it's very weak correlation, then it would be a poor idea. So in fact, there's two answers to that second part. So let's look at that again. So it's dead easy for the first part. We just substitute in our value of 75. Oh, and by the way, 75, they've also mentioned it's within the range of the scores. So this is called interpolation. We'll talk about that in a second. So first of all, the 75 is within this range of data that we had. So, if it's within the range of the data, then we've made a graph for this range of the data. Now, we don't know what happens with really, really high or really, really low scores, whether or not it's a good predictor or not. Okay, we can only really say with reasonable confidence what's happening within our data range, which we looked at. Okay, so that was kind of an important point too, which I forgot to say. But for part B, it says, since 20 is outside of the data range, there you go. They're coming up with a totally different point. It would not be reliable to predict the English grade from his humanities grade. Okay, well, I think that there's two other answers to this one. Okay, sorry. I think there's two other answers here, okay, which are valid. So firstly, they're saying 20 is outside of the range of data for the humanities examples. So maybe we couldn't use it. This is really only good for interpolation. But I think that's one answer. But I think there's two more answers. And I said that humanities is considered to be the dependent variable in this case. So we really need to swap humanities and English around. Okay, so if we've got X and Y, we really need to make the humanities and the English this way round. Okay, so that's just a problem with the setup of the formula. And by the way, this is what your calculator does. Okay, it takes X to Y. It considers that X is the explanatory variable or the independent variable there. And the other thing is, it's really important to make a mention of what R is. You know, if R is 0.1, then it's totally unreliable. Absolutely doesn't do it. Maybe they mentioned that in, yeah, they mentioned that in part A, actually. They said the data showed moderate positive correlation. So yes, we can use it, but, you know, with some caution. Okay, right, so now it does say you can find your mean, median, standard deviation, IQR and everything from your GDC. We've dealt with that. It talks about Carl Pearson here. It's about chi-squared here as well. Might be something that you're interested in. You can have a look at that test. It's a really common test, which is used. I'm not going to go into that now. There's also Spearman's rank is another really common test, which is used, but it's not in this course. And okay, so now we need to just discuss interpolation and extrapolation. Well, interpolation, we've already kind of mentioned there. It's making predictions from within our domain for which we created our function. You know, if we had, again, if we had, here's just get rid of everything here. If we had just data here, we can only really make predictions in this range here, because that's what this line is based on. And now that's called interpolation. But if we try and make predictions outside of that range, then that's called extrapolation. And that's possible to do, but it's just, you know, does this relationship still hold true? Well, the further that we get away from our lower point and our upper point there, the more issues that we're going to have in saying that that's valid. Okay. The accuracy of interpolating depends on how linear the data is, so it depends on the correlation coefficient. That's fair enough to say. The accuracy of extrapolating depends not only on the original data, but it also assumes that the relation extends outside. There's also there's another little international mindedness bit here about the Space Shuttle Challenger, which you know, which was pretty big news at the time when it, you know, blew up 73 seconds after being launched. But I'm not going to go into that now. And then now they're talking about correlation fallacies. Okay, now this is important. So especially the first one here, it talks about correlation versus causation. Now, when you have a scatter graph, if you find that you've got data which is really, really closely aligned, it doesn't mean to say that one thing causes the other thing. All that we can say is that there's a straight line relationship between the two of them. Here we go. They look down here at knife crime in London is increased, and detox juice bars increased over this period here. That would show positive correlation. It doesn't mean to say that detox juice bars are creating more knife crime. Okay, so you can't say from correlation that there is causation, that it is a causal relationship, that one thing causes the other. And that's what they're talking about here. Okay, now correlation only being linear. Now, the other thing is, if we get out R is equal to 0.1, that doesn't mean to say that there's no correlation. Okay, because we talked about this before, we could end up having correlation which is based on a different type of function. So correlation is not only linear, this is a fallacy. This is not true. That's what they're saying here. This is not true. And that's what they started off with. They're saying these are common fallacies. So falsehoods. Okay, the theory of the third variable, this one here, is this is kind of saying, well, and this is with the juice bars and the knife crime, saying both of them are increasing over time. Well, it's quite possible that although there's not a causal relationship between juice bars and knife crime, you can at least say that they've both increased over time. So if you took this third variable of time and then plotted your number of juice bars on here, then you'll find that there's also this positive relationship. And you definitely can say that over time, the number of juice bars are increasing. And it might be a factor of time. It might be that something is changing over time, which has caused this thing to happen. Okay, well, like we're talking about global temperature changes. Now, again, that might be based on CO2. It could be an IA. Could be a piece of coursework there. But okay, there could be a third variable ultimately, which is the underlying cause for these things. Okay, and a few more little points towards the end here, and this brings us up to the end of the chapter exercise here, I think, and the unit. So it says spurious mathematical relationships. So this one is saying, for example, if a relationship is required between a student's maths HL grade and total diploma points. Oh, okay, like 2020 predictions, because the maths grade forms part of the total diploma grade, and careful examinations must be made before correlation analysis can be applied. Yeah, again, we're talking about, is this a good relationship? It might be that someone's really good at maths, but really poor at a lot of other subjects. So, we have to be very careful about the causation again, and whether or not the relationship is a true one for everyone. So these are just all sensible comments to make when you're discussing this. And then combinations of separate populations, yeah. So sometimes a data set arises from more than one population, so not from one homogeneous population. Similar would mean kind of similar population rather than two distinct groups. And incorrect sampling techniques, it may be that the data has been collected poorly as well. So another consideration. Okay, guys, well, there's an awful lot of discussion there. I hope you're writing down notes throughout this chapter. You've got here 4 questions in the exercise, 5I. That's the end of this unit. There's a chapter summary which comes after that. Again, there's a lot of discussion points there. And then, interestingly, they are defining what covariance is. Okay. And then there's chapter review, of course, and they're all like exam questions, but from question 11 onwards, they're actually given with the marks as well. And it goes up to question 20. Okay, now beyond this, there's a little bit on Spearman's rank as well. And if we're talking about information which is ranked, and we're saying, well, how similar is one rank to another rank, and we've lost the original information perhaps, or perhaps this is just ranked data, then, for example, if you're getting someone testing different glasses of wine and you're getting another expert testing them and putting things in a rank, then you can do this thing called Spearman's rank correlation to analyze the relationship. And now I'm not going to talk about this now, but again, you might be interested in just reading further here. They do give you the formula, but again, it's not been mentioned in the main part of the chapter. Okay, so let's leave it there. And next time around, we're going on to trigonometry and relationships in space for Unit 6. Thanks for listening, guys, and good luck with the exercise.